Hello, this is Timothy Wood with Citadel Civil Engineering. This is CIVL202 Statics, and in this lecture we're going to be talking about centroids, connecting these ideas back to our conversation of equivalent systems. Just as a reminder, our best day to learn statics is today. This idea of centroids is going to be used throughout the rest of our curriculum. And certainly we've moved on. So we'll notice that we're still talking about rigid bodies, and we're doing something that's a little bit mathy. Statics has in it these two topics, centroids and moment of inertia, which set us up for concepts later in the curriculum. But at this point, they're going to feel a little bit mathier than we're maybe used to, a little bit more abstract, but I hope in this lecture to be able to show you how centroids is an appropriate reflection of force systems. So we're going to start with that idea of equivalent systems and work our way down to talking about areas. So to start with, we want to talk with the idea of center of gravity. So with the idea of a center of gravity, if we have this picture from the book, which you can see on your screen, we've got some body, and we want to come up with an equivalent system that has only a resultant force with no moment. Okay, so if we remember our three classes of equivalent systems, we had the complicated loading. That's what we're looking at here with the body forces. And then we could come up with the resultant force and resultant moment. Then we could take that moment, divide it by the force, and we would be able to come up with the equivalent system. Now, in this case, what we're going to be doing is exactly that. So let's take a look at this. If we're thinking about our center of gravity, we want to start by calculating our resultant force, which we said is going to be equal to the sum of the forces. Now, in this case, all of our forces are weights, so they're going to be pointing in the negative k direction, downward. And if we think about summing, well, actually, if we make all of our elements infinitesimally small, we could use integration. So some of you haven't had the calculus 2 yet, but the idea with integration is it's just a lot of summations of things that are really, really small. And so we can go further to say that this is the sum of the weights in the k direction, or the integral of the weight in the k direction, like so, and I'll pull the negative on the outside. So we can come up with this resultant force, which if we're thinking about this body, this is going to be the total weight. So that's what we're getting here. This is our total weight. What's the overall weight of this object we're dealing with? Now, the next thing we want to do is to calculate the resultant moment about our axes. So this is three-dimensional resultant moment about the origin, which we said was going to be the sum of the moments plus the sum of the r with respect to the origin cross f's. We'll notice that in this case, since we're only dealing with body forces, again, looking at that shape on the left, that this is going to go to 0. So there's no applied moments in this scenario. And that the rest of our summations are going to be of the position vector times the weight in the negative k direction, like so. So we're continuing to think our way through this. Or we could integrate it. So we would integrate with respect to the differential weight. So if we look over here, each little differential weight is going to have a position vector that's shown there that would calculate out. And if we did this, we could use our mathematical concept to break it all down, but we would get a very helpful breakdown that would look something like this. So integral y dw about the x-axis plus the integral of x dw about the y-axis. And this is our resultant moment. Okay. So that gives us our resultant moment about the x and y axes. And then we'd ask ourselves, okay, so now I've got my force and my resultant moment. How do I find the position? And the position piece is when I take my moment and divide it by the force. So this is coming up with that equivalent system. So this is going to be our main takeaway here. we're going to be able to find the center of gravity, which your textbook uses the symbol x bar. I'm going to lean toward what the FE reference handbook uses, which is an x sub c, in which we're going to take the resultant moment and divide it by the total weight, or something like this. So again, total moment, resultant moment, about the y-axis to get my x centroid divided by the total weight. And for my y centroid, again, your textbook would use the symbol y bar. We're going to use the symbol yc, integral y dw divided by integral dw. Now, the important thing to recognize here is that we haven't done anything new. This is just coming up with that equivalent system that is one force at one location. So what would that look like? Well, I don't know if anybody's ever played with one of these balance birds, but the idea with a balance bird is that you take the beak and that you can balance the bird on a fingertip. And what's happening here is that we're finding the location where we can apply a resultant force to create the reaction necessary for the balance. So it turns out that our resultant force location, or the center of gravity, is in line with the beak and slightly below the beak so that it stays stable on my finger. And what this is doing is it's evaluating in terms of a plan view. If we think about the overall mass, that we can calculate the overall total weight by integrating with respect to the weight, and then we can think through the moment that would generate motion about the x and the y axes, z coming out of the board towards you, and that we would divide that moment by the overall weight to figure out our x centroid location and then our y centroid location, which turns out to be the beak, like so. So we've come up with that equivalent system that's a resultant force at a location underneath the beak. So hopefully that makes sense to you. Now, that gives us the center of gravity. The next question would be, what about the center of mass? And if we recall, the way that we calculate weight up here, weight is just going to be equal to the mass times the acceleration due to gravity, which means that our differential weight that we're integrating by is going to be equal to gravity times the differential mass. Okay? And if we're working in a constant gravitational field, G can be pulled out of the system, and our center of mass and our center of gravity is always going to be equal to the same thing. So the idea here, again, is that my x bar, or xc, my center of mass in this case, is still going to be equal to my resultant moment about the y-axis divided by my resultant force. And in this case, that's going to be g times the integral of x dm divided by g integral dm. I pulled that g out because if it's a constant, I don't have to worry about it as an integration. And then we'll notice that these things will cancel each other out. So the gravity component goes away. And the way we might explain this is that this is my total mass moment. So now we're doing a perpendicular distance x times the mass divided by, this guy down here is the total mass. Okay? And we would have the same answer for our y centroid. So the resultant moment about the x-axis, remembering that that's perpendicular distance in this case, will be the y direction, g times the integral y dm divided by g integral dm. My g's will cancel, and so again, this is a mass moment, perpendicular distance times the mass, and then these are my total masses. So this is going to be true, except for the odd occasion in which you have a changing gravitational field across the length of the body. So that would be if you're working very close to a black hole or on a space station, be it DS9, HAL 2000, or a Romulan orbital drilling platform. So most of you aren't going to do that, in which case center of gravity, center of mass can be calculated as functionally the same thing. So that brings us to the idea of volumes. Now with volume, what we're saying here is that the density of the material needs to be constant. So if the material density is constant, as in we would look at this volume centroid and we would say the mass is equal to rho times the volume, density times volume, which tells me that my differential mass is going to be rho dV, where again, rho is my density. If my density is constant, I'm going to get exactly the same sort of equation that I got here. So my centroid is going to be equal, still an equivalent system, where I have my y moment divided by the resultant force. Just in this case, I'm now going to have two constants. I'm going to have g and rho integral x dV divided by g and rho integral dV. My y centroid like so. And again, if the density is constant, those things will cancel out for us. This is my first moment of volume. Ooh, I've introduced the idea of first. Eventually we'll talk about second moments, but that's not today. And then if I integral dV, well, that's just my total volume on the body, which is fantastic. So we're getting this going now. So what's happened is we've gone from a system where we're thinking about the weight, we divided by a constant gravitational field. Now we're talking about the mass. And if we assume it is of constant density, we're moving from physics into just geometric math. So that's kind of the beauty of this system here. Now we should talk about a couple of places where the density is not constant. Things like spray foam fire protection, potentially systems inside of engine cycles where we're changing the density of the material to move heat around. These are all things that might come into play. I'll say as a civil engineer, density is almost always constant. It's very rare that it's not. Occasionally concrete will have differing densities if we've overworked it and all of the aggregate has settled to the bottom. That's pretty bad for us. But again, CE stands for close enough. And so often we'll just assume that our concrete structures have constant density. In which case our volumetric centroid, our center of mass, and our center of gravity will all be the same geometric property. Now, one of the things that we'll note at this point is that if we have this volume centroid, for example, this cylinder here, and that shape has a line of symmetry. So in this case, the z-axis, the x-axis, and the y-axis are all lines of symmetry on the cylinder that you can see. The line of symmetry indicates where at least one component of the centroid actually is. Now the centroid's always on a line of symmetry, but it may not actually be in the shape itself. So for example, if I have a channel shape that is symmetric around a particular axis, so something like this, say this is a 3D extrusion of a channel. I'll attempt my crude 3D drawing. There's a nice little 3D drawing. Y'all like that? We notice that that looks like an axis of symmetry, and therefore that axis of symmetry is the y location of the centroid. So sometimes we can actually calculate the centroid of a shape just using inspection. So our volume centroid is always on an axis of symmetry, but it's not necessarily in the volume. So for example, if we look at this channel shape, because there's more mass over here, the center of mass is going to be shifted toward it, but the center of mass actually might fall outside of the body like so. So that's where our center of mass might be. That's our volume centroid. So the final thing we might look at is, can we take this volume centroid? So first off, this integration stuff, my guess is that for most of you, this is causing mild heart palpitations. You're not really interested in doing 3D integrations, and I don't blame you. And so we're going to work our way toward something that's a little bit simpler, which is an area centroid. So in this case, the assumption we're going to make, we've gone from constant gravity gave us center of mass, and constant density gave us center of volume, or volumetric centroid. To go from volume to area, we can think of a shape that has constant thickness. Now, this is not all the time, but sometimes we'll have a shape with constant thickness. So the thickness times the cross-sectional area. So for our prismatic shape, that would give us the overall volume. Consider something like this, right? So I have a complicated looking shape, but it's prismatic. It has a constant thickness. So if I do my cross-sectional area times the thickness, I would get the overall volume. So what this is going to tell me is that my differential volume is going to be equal to the thickness times the differential area. Or if we wanted to tie it all the way back to talking about weight, if we have a prism, we can solve for the weight as gravity times density times thickness times area. So if we do it differentially, we can say differential area like so. And if the thickness is constant, so if it's prismatic, we can actually get our way to this area centroid. So this is actually the thing that we'll spend time calculating, where our x centroid is going to be equal to, still, it's an equivalent system, so our resultant moment about the y divided by the resultant force, just that in this case we're going to have g and rho and t, the integral of x dA divided by g and rho and t, integral of dA. Yc is equal to the resultant moment about the x-axis divided by the resultant force, g and rho and t, integral y dA, and g and rho and t, integral of the differential area. And we'll notice here that our density, if these things are constant, meaning we can pull them out of the integrations, our density, our constant gravitational field, and our thickness can all be canceled out. And we would now call the numerator the first moment of area, and the denominator the total area. And the net result is that you get those equations that you can see there, where we can either do this by summation or by integration. So this gives us our full discussion of centroids. Naturally, this information is available in your textbook and in your FE reference handbook, where you can find these equations over here from the slide. So again, we have center of gravity, where we started calculating our resultant force and moment at a particular location. We divided the moment by the overall force, and we were able to find center of gravity. That allows us to do an equivalent system of a force at a location. See, there's no moment here, right? So that my balance bird will stay in place. Now, if we're in a constant gravitational field, which is most of the time, we can pull out that gravity constant, cancel it out, and we can take the first moment of mass and divide it by the overall mass. If that material is of constant density, we can relate the weight all the way down to just the volume itself, and we'll have the first moment of volume divided by the total volume to find the volume centroid. If the shape is prismatic, prismatic with a constant thickness as well, we can come in here and calculate the first moment of area divided by the total area, which is the mathematics we're actually going to do in this class to solve some homework problems. That said, the integration is probably not your most exciting thing. We'll have some videos to talk about that, and in class, we'll analyze this shape and find its centroid. I look forward to talking to you in class, and I'll see you then.